Hi everybody. Sorry about the delay there. Welcome to the last lecture, where we'll cover exciting things such as dilutions, and math, and all the things you need to know for the lab. So we're going to spend the period tonight finishing the slides, and then whatever time is left over, we're going to just talk about the lab. So let's get started. Before we do the dilution section. Let me go over the things that are due and are upcoming and whatever. We have a quiz due tonight. That's for units 13 and 14. I don't remember if I unlocked the unit 15 or 16 quiz. I'm going to do all of that tonight, along with opening up the exam and setting the deadlines and stuff. I just haven't had time. And then after work, I was answering emails and then forgot. I had to go make dinner or something, and then I fell asleep. But I'll have time to do that tonight. So I'll get that done. But quiz 8 in the meantime, make sure you do that tonight. That is a soft deadline, so you do have tomorrow. Lab worksheet number 5. I know a few people approached me saying, "Oh shit, when is this due? Is it due tomorrow?" No, it's due next week. You guys read the syllabus, right? I mean, it's a little late to be asking you that on the last day of lecture in week 10. But lab worksheet number 5 is due Tuesday on the 15th of June. That is apparently the day before the final exam, because you don't want to be doing it on the day of the final exam. Although, with how deadlines work in this class, if you need an extra day, that extra day is the same as your final. I wouldn't do that. So try and get it done early. Also, it's good review for problems that you might see on the exam and the final. So, finally, course evaluations. Those are due Friday. I have absolutely no input or control over those in any way. So please, please, please make sure that you get those done before Friday, because after that, I just can't help you. Okay? Extra credit if 80% of the class does it. So, easy points. Yours if you want them. All right, here's what we're going to do. We're going to dilute solutions. We're going to take a concentrated solution. We're going to add water to it, because if you have a concentrated solution, and I'll just kind of draw that with a little beaker here. So here's my solution. It's real concentrated, which is why the lines are really thick. But if I add water to that, so we'll just toss in some water, and we'll put about this much. Then what the solution will look like is now its volume will be up here. But that same amount of stuff in there will be far less concentrated. So we'll go from concentrated to dilute. So that's the logic behind it. If you wanted to go from dilute to concentrated, you could boil the water away, assuming that your solute was non-volatile. So it'd have to be like an ionic compound or something that wouldn't evaporate. If you tried to do... Ooh, excuse me. I took a drink of water and then I hiccuped at the same time. That was inopportune. I realized that my headset is not out. I don't know if you heard any of that. I hope you heard some of that. Let me know if you couldn't hear me. I was trying to talk pretty loud. If you wanted to go backwards and concentrate a solution, you could boil it, but if you had something like ethanol and you were trying to concentrate it, then what would end up happening is the ethanol would also evaporate, and you'd get a mixture, and the concentration would change. So obviously that's no good for this sort of process. That's called distillation. That's something that you can read about on, like, various moonshine blogs, I guess, or something like that. But we do talk about it in organic chemistry when we actually have you do distillations of stuff. So what's the formula for diluting a solution? It's this. Now, there are all sorts of variations on this formula from various textbooks, so here's one. You might see M1V1 equals M2V2, or you might see this. They're all the same thing. C and M are just concentrations, and V is a volume. So we're going to stick to the one that's in your text, which is the one that you see right here. And we're going to use this. But first we need to explain what the variables do. So take a look at those for just a second. And then I'll explain them, because this is pretty self-explanatory if you have been following along. Okay, so what might S be? And what might D be? Well, we're trying to dilute stuff, right? So D is dilute. What is S? S is the stock solution. The stock solution is what you start with. It's in the stock room. Think of it like in terms of cooking. If you're cooking with chicken stock is concentrated chicken broth and all the good stuff in there. And then you can either dilute it by adding water, although I don't know why you'd want to, or you can concentrate it by putting it on the stovetop and then reducing it with heat. So M is always a molarity, and V is always a volume, and the volume can be whatever you want it to be, believe it or not. Whatever, right? You might think, well, wait a second, that's not going to cancel out with molarity. But that's actually not the point of this equation. And you'll see that in a second here. So let's put all this together. So MS must be the stock, or in other words, starting concentration. VS is the volume of stock solution needed. Over here, MD is the dilute, or ending concentration. And VD is the volume of dilute solution made. Now, generally speaking, this value is fixed. This is whatever is written on the bottle. You can't change this number unless you order a different solution. And that's expensive, and it takes like 3 days, unless you pay for expediting shipping. And logistics won't cover that. Not unless there's a dire emergency and you need it tomorrow. But we don't. We can plan ahead. These numbers over here, you get to choose. So maybe I want a 1 molar solution, and I need 10 liters of it, because I'm going to make it for all of the students who are going to take Chem 140 this quarter. 10 liters might be enough for everybody to go through. Or maybe I'm trying to plan ahead and I want to make 50 liters so that I can do this for the entire year. And we'll just put it in the stockroom because we have tons of space to put bottles on shelves. You get to pick what numbers you want. That means that this down here is oftentimes what we're going to solve for. I grabbed the wrong pen there. So. Now, you're not always going to solve for VS. If you are doing a prep, then yes, VS is the one you're solving for. But if you're just answering a general question to get accommodated with this formula, I might ask you any number of things. Because once you know 3 of these variables, you know the 4th one, right? You could solve for it. All right, so now that we've talked about those, let's do a few problems for practice. So let's suppose in the stock room, I have 10 molar calcium chloride. But I don't want 10 molar. That's too concentrated for the activity that I have planned for the lab. I need 0.5 molar calcium chloride, and I'm going to need about 3 liters of it. What should I do, and how much of the 10 molar stuff do I need to dilute in order to prepare the solution? Now, whenever we prepare a solution, just like with the solid solution before, we're going to have a flask. I don't know what happened. I can't draw flasks. That's just something I'm not good at. Okay. So there's my mark. And this flask is going to be 3 liters. I'm going to select a flask that has the volume that I want to make. I have the 10 molar calcium chloride. And I have as much of it as I need, presumably. So let's take the equation. Oh, I did 1s and 2s because I'm used to doing that. And what we're going to do is I'm going to make a little chart.
And the way that you read this chart is you just read the coordinates. So whatever goes in here would be MS. Whatever goes in here would be VS, MD, and VD. And so making this little chart is a convenient way for you to organize these types of problems, because one of the things that gets people when they're starting out and doing these types of problems is they get overwhelmed by the numbers. They don't know how to sort through the information that is presented to them in a clear and concise manner. And if you make these little charts, that can help you. So we know that the stock solution is 10 molar. So that's this right here. And I know that the solution I want to make is 0.5. Oops, I put it in the wrong spot. Sorry. Molar. And I want to make 3 liters of the 0.5 molar solution. So I need to solve for that variable. So let's do that. We're going to solve for VS. So I'm going to do the algebra, and you don't need to see me divide by MS. We can all do that. And I'm going to enter the numbers in now. So the dilute molarity was 0.5. The dilute volume was 3 liters. And the concentrated molarity was 10 moles per liter. Now I cancel the units. These units cancel out, leaving me with the volume of the stock solution that I need in liters. We'll grab the calculator. 0.5 times 3 over 10. And I get this many liters. Now, let's suppose that instead of 3 liters, I wrote this. I gave you a volume in milliliters. And so your equation would then change, wouldn't it? And so now when we do this expression, the answer ends up being in whatever units are left. So that's this. And you'll notice that this number and the answer we got before, exactly the same, right? So you don't even need to put all the volumes in liters for the dilution formula. You use any volume you want. Whatever volume you put in is what your answer will be when you get it out. You could put in cubic kilometers if you wanted to. Please don't. So this formula is very versatile and can be used for virtually any application that you want to, as long as whatever concentration units you put in match, and that whatever volume units you put in match. You're always going to cancel out one of them, and then you'll get the other one that you're solving for. So this will be particularly helpful because later on in 161, we'll do an experiment where I give you concentration of ethanol, but I don't tell you its molarity. I just write concentration, 5%. And so you could just use arbitrary units and just say, okay, 5% is my initial concentration. My final concentration is whatever it ends up being when I dilute by a factor of 5 or something. Okay, so now that we know how much of the stuff that we want to put in there, we can now write our preparation. So we'll do the same thing that we did yesterday. So step 1 is to add the stuff that we calculated. So that'd be this, 150 milliliters of, what was this of? Well, it was of the stock solution, right? Of 10 molar calcium chloride. Where does it go? Do we dump it in the sink? Do we throw it in the air? No, we put it in a 3-liter volumetric flask. Then we just do the rest of the steps just like we did before. So step 2 would be add H2O. to the mark. Step 3 is to mix well, 50 times. And then, of course, step 4 is enjoy. So that's the verbal description of the procedure. Here's the pictorial one if you'd like to see that. That looks like this. Now, same deal as before. You want to pour all the water into the rinsing cylinder because you're working with a liquid. Some of it's inevitably going to get stuck on the sides. So rinse this out really well into the container. Rinse the funnel really well. And then add all the water until you hit the dilution mark at the very top. And then cap the lid and mix it really, 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 really well, and you'll have a homogeneous mixture. Now, down below, you can see this calculation that the concentration and the volume used will have some number of moles of calcium chloride in there. The concentration and the volume of the dilute solution will have the same number of moles. And that's by design. We found that the solution that we want to make has X number of moles in it, and thus we can calculate the volume that would also have that many moles of if the solution is stock solution. So that's what we're doing. We're just doing moles equals moles. Moles before equals moles after, and all we're adding is water to do a dilution. Okay, so I've done it with the example solution. I want you to make 1 liter of 1 molar HCl from 14 molar HCl. This is the stock solution that we buy from a vendor. This is as concentrated as HCl can get. It does not come any concentrated or any more concentrated because you can't physically do that. So we need to dilute it. 14 molar is so acidic that it will dissolve virtually anything. Like if you poured this on paper, it would eat a hole through it. If you poured this on your hand, it would burn like crazy, and you'd have to put your hand under cold water for 15 minutes. You don't want to spill this stuff on you. This is 14 times more. It's 140 times more acidic than your stomach acid, for example. That's too acidic. We need 1 molar HCl for whatever experiment we're going to do. How do I make it out of this? Follow the procedure that we just did over here. Oops, sorry, I'm in the wrong screen here. Ah! That was a sound that I made. Follow the same procedure that we did over here. You can go back in the video and review that if you need to. And tell me how much HCl from the stock solution I need, and then describe in words or pictures how to make that. Okay? Type your answer in the chat when you're done. I'll give you about 5 or 6 minutes to puzzle it over, and then we'll go over the solution together. 2 more minutes. We'll go over the answer. All right, let's give this a shot. That's the wrong button. There we go. All right, so I'm going to make my little grid here. So M, V, S, D. There we go. So my stock solution is 14 moles per liter. And I want to make 1 mole per liter of solution. And I want 1 liter of it. So I can do my dilution, and I get the following equation. And then we'll just plug in the numbers. So dilute molarity is 1 mole per liter. I want 1 liter of it. And my stock solution was 14 moles per liter. So I type in all of those numbers in my calculator, and I get 0.0714 liters is my volume of stock, or 71.4 milliliters. So now I can write the procedure. So my procedure to dilute this would be to 1, add 71.4 milliliters of 14 molar HCl to I almost put to a 1 liter flask. Step 2 is to add H2O to the fill line. You can see the answer coming in on the side there. Then mix it real well and enjoy. So there you go. That's how you make this solution. All right, I have 2 more practice problems for you to try. Oops, there we go. So I'll give you 5 minutes to try these. We'll go over those answers, and then we'll talk very briefly about part A of the lab before we take our break. Okay, so try these 2 problems. So the second problem is similar to the problems we've just done. Problem 1 is a different problem, and it's asking you, what volume would you dilute 0.2 liters of a 15 molar sodium hydroxide solution to get a 3 molar sodium hydroxide solution? You're not solving for the volume of the stock solution in this case, because I gave it to you, right? I told you how much stock solution you have and are adding water to. So make your grid, see what you're solving for, and then solve that problem. Okay? So again, there are other types of problems out there that we can use this expression for. All right, good luck. We're all counting on you. I'll see you in about 5 minutes. All right, 2 more minutes and we'll go over the answers. All right, let's go over the answers here. So let me clear all this out real quick. So for this first problem, we'll set up our little grid. And so I have a 15 molar NaOH solution, and I have 0.2 liters of it. And I want a 3 molar solution, but I don't know how much water to add to it or what the final solution's volume should be. So we'll solve for this. And this is trivial to do the algebra for. And so we'll plug in all the numbers. So my stock solution is 15 moles per liter. My volume was 0.2 liters. And my dilute volume was 3 moles per liter. So I get 15 divided by 3 is 5 times 0.2 is 1 liter. So if the final solution's volume, or if the solution's final volume is 1 liter after I've added water to it, it will then be 3 moles per liter concentration. All right, and then how much sodium nitrate solution is needed to prepare this solution? So for the second one, we'll set up the chart again. So the stock solution is 6 molar, and I want 1.20 molar solution, and I want 0.525 liters of that. So again, we'll do the calculation same way. So dilute 1.20 molar. Volume of the dilute 525 milliliters or 0.525 liters divided by the stock solution molarity is 6, and that one I have to punch in my calculator. It's going to be like 0.1 or something, right? 1.2 times 0.525 divided by 6. 0.105 liters. So I would prepare that solution by first pouring out 105 milliliters of the stock solution. There you go. All right, now how does this help us do the lab? So let me get the lab up real quick. I'm not scrolled to the right spot. So you should be able to do the pre-lab questions, no problem. But we do want to talk a little bit about the lab. All right, so we don't need any of that. We'll just scroll over here. So for part A, you're going to be making a solution out of solid sodium hydroxide. So number 7, you need to figure out how to prepare a 0.2 molar sodium hydroxide solution with solid NaOH and 250 milliliters. We did that on Monday's lecture. So you can review the lecture slides on how to do that. Use the molarity and the volume to figure out moles, and then figure out moles of solid, or grams of solid sodium hydroxide using the molar mass, and then describe in words how to prepare the solution. You'll type the answer in. The vinegar part involves the dilutions that we are doing today. However, there is a bit of a catch. And that is, I'm going to give you the stock solution, which is concentration 0.8261. And then I'm giving you these vague sort of dilution factor terms. And so what is meant by this is, let me clear this out of the way real quick. And then we'll get... where did it go? Why can't you find it? Yeah, there it is. Okay. For some reason, it wasn't showing me that. Boop. All right. I'm trying to make this bigger, but also not use up half of my screen real estate here. There we go. Okay. So how does this work? There we go. So what is meant by dilution factor is that if I had a solution with dilution factor 2, then I would take the original concentration and divide it by 2. And so the diluted solution would have a concentration of, looks like 0.4131. This would be my diluted concentration. Or in other words, this is MD. Now, if I want it to be a 3, well, I put a 3 here. And then I would just do the numbers. So 0.8261 over 3 is 0.275. Okay, you could do that for 5, 7, and 10. That's not difficult to do. So I'll leave that part for you to do. But now what do we do with it? Next it says, tell me how you would prepare solution B. That's this solution right here. So what I'm going to do is I'm going to show you how to prepare solution A. And then you can do the same process for preparing solution B. So let's prepare solution A. So I know that the stock solution is this because the lab tells me. Actually, you know what I should do? I should make a chart. There we go. So we know that the stock solution is 0.8261 because it told me that. You just solved for the dilute concentration. Oh, I actually get another sig fig, so I guess I'll just throw it in there. So there should be a 4. And you know that you need to prepare 100 milliliters because the lab procedure tells you to do that right here. It didn't highlight. There we go. right at the top there. Prepare 100 milliliters of diluted solution. Okay, so we'll do that. So I need to figure out how much stock solution I need to do the calculation and prepare the solution, right? And you've done this like 74 times already today, so we'll do one more. So my dilute concentration is this. My dilute volume is 100 milliliters. Remember, the volume units don't matter. You don't have to change it to liters because you'll just get milliliters out. And the stock concentration is 0.8261. And when I put this in the calculator, I should totally get 33.3, right? Yeah, 33.3 milliliters. There you go. So I did the calculation for how to prepare solution A. You actually had to do the calculation for all 4 of them. So you should get a volume of stock solution needed to prepare all 4 solutions. And then for solution B, I want you to write the procedure of how to prepare that solution in the box, which would just be, so for solution A, for example, I would take 33.3 milliliters of stock vinegar, 0.8261 moles per liter, put it in a 100 ml flask, add water to the mark, and mix 50 times. There you go. That's part A. So we've done part A completely, and we've done the dilution section completely. So we're ready for the next part, which is part B. And we're going to do that after we come back from the break. So when we come back, we're going to start. Oops. We'll hide this for now. We're going to start up again here in molarity and stoichiometry. I'm going to show you how to do a titration. And we'll get to that in just a little bit. So I'll go get the music back on, start the timer for a 10-minute break, and I'll see you in just a little bit. All right, we are back. So let's do the last section in the class. So the only new topic that we're introducing here is we're just combining all the stuff we learned about molarity with all the stuff we learned about stoichiometry and doing a different approach to it. Everything else in this section is exactly the same. So the real trick to this is knowing that you can turn a volume of a solution into a number of moles by using the concentration. Because remember that volume times molarity equals moles. And there's how the units work out. Oops. Provided that your pen doesn't, catch. There you go. So what that means is that, remember this diagram that we were doing before? Now what we can do is we can add volume to it. And I can ask you questions that are like, okay, here's a balanced equation. I'm going to react this many milliliters of this concentration solution. How much product will I make? And otherwise, it's exactly the same type of stuff that we've done before. Our diagram's a little bigger now. So let's look at this. This is the neutralization of phosphoric acid with sodium hydroxide. You make sodium phosphate and water. Let's suppose that I use 4.9 grams of phosphoric acid. How much sodium hydroxide do I need to react completely with it? Well, I am working with a mass of phosphoric acid, so I'm going to start here. A is going to be phosphoric acid. What's B going to be? I want to know what volume of 0.250 molar sodium hydroxide. So I need a volume, so I'm going to go here. That's my objective. I'm going to turn grams of A into moles of A. So grams of phosphoric acid into moles of it. Then using the balanced chemical equation at the top there, we'll turn moles of phosphoric acid into moles of sodium hydroxide. And then we'll turn moles of sodium hydroxide into a volume using the molarity. And it turns out this is actually very trivial to do now that we've done all of this work on molarity and stoichiometry. We just have to do what we were doing before. Oops, we also have to get rid of that. We just have to do what we were doing before with one extra step. And so let's throw that step in there. So there's our question. Clear the board here. All right, so I'm going to start with grams of phosphoric acid, moles of phosphoric acid is our next step. We'll turn that into moles of NaOH, and then moles, or not moles, but a volume of sodium hydroxide. So let's write down all the relationships that we know. So I know that in 1 mole of phosphoric acid, there are some number of grams of phosphoric acid. And you can look that up on Lentech. So let me go do that real quick. "98 grams per mole." Okay. For the moles of phosphoric acid to moles of sodium hydroxide, I just use the balanced chemical equation. So moles of phosphoric acid equals moles of sodium hydroxide. And I just grab the coefficients. What's the coefficient for phosphoric acid? 1. So for every 1 phosphoric acid I put in, I also put in 3 moles of sodium hydroxide, because the equation is balanced and tells me that. And then finally, for the molarity relationship down here, moles and volume, moles of sodium hydroxide in volume of sodium hydroxide. So that would be liters. Liters of sodium hydroxide. And I know that with the concentration shown, I put 0.250 moles per liter. So my molarity becomes a relationship. And now I can just do the calculation as shown. So I got 4.90 grams of phosphoric acid. We're going to turn that from grams into moles, just like we have done before. We'll turn moles of phosphoric acid into moles of NaOH, like we did before. And then finally, we'll turn moles of NaOH into a volume. And now we're just going to fill in the numbers. So how many grams were there per mole? 98. So 98 grams per mole. For every phosphoric acid I put in 3 moles of sodium hydroxide. So 1 phosphoric acid, 3 sodium hydroxide. And then how many moles per liter? This many moles per this many liters. It looks weird that it's upside down, but don't worry about that. Just put in the numbers where they belong. And then we'll just calculate the whole answer, and I will get a volume of sodium hydroxide. 4.90 times 1 times 3 times 1 divided by parentheses 98 times 1 times 0.250. You don't have to put in the times 1s, I just say them. And I get 0.600 liters. So 600 milliliters is required to completely react with this acid. And wouldn't you know it, that's the right answer. I'll leave the work on the screen for just a second, though. All right, so that's one. How many of these do I have? Because I do want you to do one of them on your own here. I have 3. Okay, so we'll do the next one together, too. So let's do the next problem here. All right, so this is the same sort of principle. I'm reacting calcium hydroxide with nitric acid. I have a different balanced equation. I've already balanced it for you. What volume of calcium hydroxide, 0.125 moles per liter, would react completely with 15 milliliters of 0.225 moles per liter nitric acid? So here's the ones that I know. So I know a volume, and I know a molarity. So I know the moles of this one. So this is going to be my A. So A is nitric acid. B is going to be the other thing. And it's asking for a volume, so we're going to solve for that. Excuse me. So we're going to turn volume into moles. Then we're going to turn moles into moles. And we're going to turn that moles into a volume. Excuse me. So let's do that. So let's write out our blueprint here. So volume of nitric acid, moles of nitric acid, moles of calcium hydroxide, and volume of calcium hydroxide. And let's write in all our relationships here. So I know that in some number of moles of nitric acid will give me a volume of nitric acid. And that relationship is, it's 0.225 molar nitric acid, so there must be 0.225 moles per liter. We can do the other molarity while we're thinking about molarity here. So how many moles of calcium hydroxide are there in how many liters of it? Well, in 1 liter, there are 0.125 moles of calcium hydroxide. And then this part is just stoichiometry. Okay, how many moles of nitric acid to how many moles of calcium hydroxide? Well, according to the balanced equation, I need 2 of these for every 1 of those that I have. All right, let's write it all in. So I'm starting with 15 milliliters. Now, obviously, we're working with liters, so we're going to need to convert that to liters. So I'll just do this. So 0.00150 liters. Everybody knows how to turn milliliters into liters by now, I hope. It's the last lecture. If not, you needed to have asked me questions about that ages ago. All right. We're working with nitric acid to start. So we'll turn a volume into a molar. Using the molarity, we'll turn volume into moles. Then we'll turn moles of HNO3 into moles of calcium hydroxide. And then we'll turn moles of calcium hydroxide into a volume of calcium hydroxide. Now you'll notice that I don't use the indicator for volume. That's because if I wrote calcium hydroxide up here, you might be tempted to cross out the calcium hydroxide up there with something else and do the units wrong. So when you're given a volume, be very careful you're using the right volume. Let's go fill in the numbers. So there are 0.225 moles of nitric acid per liter. There are 2 nitric acids per 1 calcium hydroxide. And the concentration of calcium hydroxide is 0.125 moles per liter. So this will give us a volume in liters. And I'm punching it all in my calculator, and I got 0.0135 liters, or 13.5 milliliters. So that's the volume of calcium hydroxide that would react completely with 15 mils of 0.225 molar nitric acid. There you go. And then for some reason this goes after the answer. I don't know, I gotta fix that. All right, so now I want you to try these. I'm gonna give you this reaction. Notice that we're doing a lot of acid-base chemistry here because the lab is basically this. You're gonna react an acid, vinegar, and then later sulfuric acid with the base that you've prepared, the sodium hydroxide. So that's why we're using lots of hydroxides and acids here. All right, so for the first question, we're going to use 52 grams of iron 3 hydroxide. What volume of 1.50 molar HCl will react with that? And how much FeCl3 will be made? So the bottom question, how much FeCl3 will be made, is actually a unit 14 question. So I'm not going to deal with that today. I'm going to just answer the first one so that we have enough time to talk about the lab, because the lab for part B is much more involved. But fortunately, we're all done with the content here. So we can just talk about the lab for 30 minutes and we'll be done. So do this first problem. You do the second one on your own. I'm going to do the problem in the background here, and I'll just post the answer for the FeCl3 one. So you can do it on your own. But do the first one, and then we'll go over that together. So there's the answer to the second one that you can just do on your own if you want. But we're going to go over the first one together once you have done it. So 5 or so minutes. 2 more minutes. All right, let's go over the answer here. So, oh, there's my work for the previous problem. You can see that real quick. You can just pause the video there. And it's gone. If you want to see that solution written out. All right, so we are using solid sodium, or not sodium, iron 3 hydroxide. And I want to find the volume of HCl that will react with it. Well, we're going to turn grams of iron 3 hydroxide into moles. We'll turn that into moles of HCl, and then we'll turn it into a volume. And let's write down all the conversions. So in 1 mole of iron 3 hydroxide, there are, and I just had this, and I of course erased it. Where is Lentec? There it is. So FeCl3. Oh, we don't need FeCl3 anymore. FeOH3 is 106.87. So 106.87 grams of iron 3 hydroxide. And then for moles of iron 3 hydroxide, moles HCl. For every 1 iron 3 hydroxide I put in, I also put in 3 moles of HCl. And then the molarity of the HCl is 1.50 moles of HCl per liter. And let's do the calculation. So 52 grams of iron 3 hydroxide. FeOH3 grams turns into moles FeOH3. Oops, I forgot my parentheses there. Mole. There we go. Then moles of FeOH3 to moles of HCl. Just following our blueprint that we have here. Moles HCl per liter. Then we'll fill in the numbers. So in 1 mole, there are 106.87 grams, like we set up here. For every 1 iron 3 hydroxide we put in, we also need 3 HCl. And then 1.50 moles per liter. And what does the calculator say? 52 times 3 over 106.87 times 1.5. 973 milliliters of solution, or 0.973 liters, whichever one you want to use. So there you go. That's the answer. All right, so now how does that fit in with, and I gotta go find it again. Oh, that's not what I want. I clicked a link and my image went away. So there we go. So this should now window capture that, and it should still work. Oh, I captured the wrong window. How about this one? There we go. All right, let's talk about part B. Part B is a titration, and what that means is that I am adding controlled amounts of liquid reagents with known molarity to some stuff that I want to react it with. So, for instance, in question 10 here, I am reacting sulfuric acid with sodium hydroxide. So, you should be able to write out the balanced equation for sodium hydroxide and sulfuric acid because you know what those things are and you know what the products should be based on the discussion that went up before. You should end up with water and sodium sulfate because the H and the OH react. And we talk about that a little bit up here in the conversation for like what a titration is, what a burette is, and so on and so forth. Oh, there's the reaction right there. So this is the reaction that we're doing. Now, when we do the chemistry, we add a certain amount of volume in there. And so that's what this says. So initially, the level is at 0.2. When it's done, it's at 15.78. The volume that was used is the difference between the initial reading and the final reading because of how a burette works. And you can read about that in the documentation. So the volume of sodium hydroxide used for this first trial, for example, would be 15.58. You're going to figure out the volume used for each trial and get an average. And once you know the average volume of sodium hydroxide, you can then do the stoichiometry like we just did. So let's look at an example. So let's suppose that, hopefully this will capture right. Yeah, there we go. So let's suppose that we're looking at just trial one. You're going to be looking at the average here. But the process that you're going to follow is the same. So V initial is 0.20. V final is 15.78. So the volume that was used will be the difference between those. So be careful of sig figs. You should have 4 when you're done with this because of how subtraction works. Don't round it to 2. I'll be sad. Okay, so this is the volume of sodium hydroxide. Now, for this question, you do kind of have to look ahead to see what it's asking you to eventually do. Because on question 13, it says calculate the molarity of the sodium hydroxide solution determined by each trial, and then calculate the average. So we're going to figure out the molarity of trial 1 by doing this. Now, I have told you that the reaction uses 25 milliliters of 0.0750 molar sulfuric acid. So I know that the volume of sulfuric acid is 25 milliliters. And I know that its molarity is 0.0750 moles of sulfuric acid per liter. Now remember, since I know volume plus or volume and molarity, I know moles. So if I need to figure out the molarity of sodium hydroxide, I can use all of this information to do that, and the balanced chemical equation, which is just 2 sodium hydroxide plus sulfuric acid, makes other stuff that we don't care about because we're not concerned with that part of the reaction. So we want to use this to solve it. Now, this is a little bit different than what we've done before, because normally I give you the molarity and we're going to solve for the volume. But in this case, I gave you the volume. So let's go through the problem and just see what happens, right? So we need these numbers, but they're already written up at the top. So I'm going to do the calculation here. So if I take the volume of sulfuric acid, and I turn that into moles of sulfuric acid, then I can potentially determine the number of moles of sodium hydroxide that are used, right? So we're going to do that. So I'm going to use 25 milliliters. I'm going to turn that into liters. And then I'm going to multiply that by the molarity of sulfuric acid. And then I can turn moles of sulfuric acid into moles of sodium hydroxide. And that will give me this. Now we'll just fill in the numbers. So up above, there are 0.0750 moles of sulfuric acid per liter in the data table. It's highlighted right there. And I know from the balanced chemical equation that for every 1 sulfuric acid I use 2 sodium hydroxide. So when I punch in all these numbers, I get 0.02500 times 0.0750 times 2. And I get this as my answer. So in the titration that we did for trial 1, that's the number of moles of sodium hydroxide that were used. Now, I know the number of moles, and I know the volume, don't I? The volume's right here. So if I know the number of moles and the volume, how do I get molarity? Well, we know that molarity is moles over volume, right? So if I just type this number in, divided by the volume that we used, which was 15.58 milliliters, got to turn that to liters. Then my units will be moles per liter. So I will get a molarity. So I just divide those two numbers together. And I get this. Oh. There you go. So that's the molarity of the sodium hydroxide solution used in trial 1. So you should be able to do that for trials 2 and 3, and then take the average and report that for the answer to number 13. Note that it doesn't go in the data table. You're just going to report that as your answer. There's no slot for molarity in the data table. Now, when you get to the next question, it's going to ask you, for question 14, well, we prepared this solution, 0.200 moles per liter, we thought, but our actual answer was 0.2407. Calculate a percent error. You know how to do percent error because that's from a previous chapter. Now, there should be an enter right here. So this line right here is actually everything below this is not part of question 14, so just mind that. But for questions 15 and below, at the very start, it refers right here. We're going to use the vinegar solution with dilution factor 5. So that's solution B that you prepared up here. So you have to go back to question 8 and get your number from that. That's the concentration that you would expect it to be. Then what you're going to do is you're going to titrate using the sodium hydroxide that was used in the previous section. So whatever your answer was for 13, calculate the average molarity, which you will have calculated after you've done all the 3 examples that we just did. Trial A. You can do that for B or trial 2 and trial 3 and get the average. You're going to take that number and you're going to enter it right here. This is your molarity. It goes in this box. So whatever you get from question 13 goes in this box. Then you do the same process, except now you know everything about sodium hydroxide. You need to solve for vinegar. So figure out the volume of sodium hydroxide used. You know its molarity because that's the average from problem 13. So you know the moles of sodium hydroxide used. Use the balanced chemical equation to tell me how many moles of vinegar are used. And then knowing that you put 25 milliliters of vinegar in there, calculate the actual molarity that the titration says. And then you'll get another percent error for question 19 down here. Whatever your answer was that you got for the molarity of the vinegar compared to what it should have been from question 8b. All right. So you're going to be doing a bunch of these calculations like we've done in this last section, just over and over and over and over and over again. And if you get stuck, let me know in the Discord, and I'm happy to help you with that. The analysis questions are just more titration questions. And that's it. So for this experiment, I'm going to be grading you on, did you attempt to do it, and is your answer relatively close? So normally I grade it as in, like, if it's incorrect, I highlight it yellow, and then you don't get points for it. This time I'm going to highlight stuff yellow still, that is too far off. But if you're close enough and it looks like you're on the right track, I just give you points for it. I'm not going to grade sig figs because I just don't have time, unfortunately, at this point. Because I'm going to have 150 labs that are all going to come in this week, and I have to have them all graded by Monday. Because grades are due Tuesday, and if I don't upload grades by Tuesday, Carl gets really mad at me. And you don't want to piss off Carl because he's like a saint. He keeps the entire school running with all the grades and all the stuff. He's the registrar. So I don't want to make Carl unhappy. So I do have to grade these really quickly. I will make every attempt to return them, but it probably won't be until after grades are assigned and uploaded. So there won't be a chance to, like, argue for more points on that or do much with it at all, really. But that's how you do a titration. We just do these sort of stoichiometry calculations that we've been doing in this last section. So, oops, we can get rid of this now. All right. I think that might be it. Yeah, that might be it. Oh no, I clicked on something and ruined it. We'll do it again. Hold on. That's all I have. Congratulations, you've reached the end of Chem 140. There's nothing left for me to teach you. There's nothing left for you to do other than... Actually, there's plenty for you to do. There's nothing left for me to do. My job at this point is just to help you with any questions you might have. And that's what tomorrow is for. So tomorrow is a review session for exam number 2. Again, exam number 2 covers units 9 through 16. So everything all the way up to this moment in time. So yes, there will be stoichiometry stuff on the exam. I'm going to open up quiz 10 tonight. Again, quiz 10 is for practice. It's worth 1 point. You check a box somewhere in your quiz. that gives you a point. Please check the box. Don't not check the box. And do the practice. Do the quiz for practice. You get 2 attempts. I would recommend doing it before the exam, but do it whenever you want to. It's fine. And then, yeah, I will see you tomorrow for the review session. So, yeah, that's all I got. Have a wonderful rest of your evening, and we'll see you tomorrow for any questions you might have. Take care, and good luck on the exam number 2.